Russia is powering up a giant laser to test its nukes. To check that atomic weapons work, scientists run simulations of explosions using high-energy lasers, and Russia is building the strongest one of all. In the closed town of Sarov, roughly 350 kilometers east of Moscow, scientists are busy working on a project to help keep Russia's nuclear weapons operational long into the future. Inside a huge facility, 10 stories high and covering the area of 2 football fields, they are building what's officially known as UFL-2M, as the Russian media has dubbed it, the Tsar Laser. If completed, it will be the highest energy laser in the world. High-energy lasers can concentrate energy on groups of atoms, increasing temperature and pressure to start nuclear reactions. Scientists can use them to simulate what happens when a nuclear warhead detonates. By creating explosions in small samples of material, either research samples or tiny amounts from existing nuclear weapons, scientists can then calculate how a full-blown bomb is likely to perform. With an old warhead, they can check that it still works as intended. Laser experiments allow testing without letting a nuke off. It's a substantial investment by the Russians in their nuclear weapons, says Jeffrey Lewis, a nuclear nonproliferation researcher at the Middlebury Institute of International Studies in California. Until now, Russia has been unique among the best established nuclear powers in not having a high-energy laser. The United States has its National Ignition Facility, NIF, currently the world's most energetic laser system. Its 192 separate beams combine to deliver 1.8 megajoules of energy. Looked at in one way, a megajoule is not an enormous amount. It's equivalent to 240 food calories, similar to a light meal. But concentrating this energy onto a tiny area can create very high temperatures and pressures. France, meanwhile, has its laser megajoule, with 80 beams currently delivering 350 kilojoules, though it aims to have 176 beams delivering 1.3 megajoules by 2026. The UK's Orion laser produces 5 kilojoules of energy. China's SGII laser, 180 kilojoules. If completed, the Tsar laser will surpass them all. Like the NIF, it's due to have 192 beams, but with a higher combined output of 2.8 megajoules. Currently, though, only its first stage is launched. At a Russian Academy of Sciences meeting in December 2022, an official revealed that the laser boasts 64 beams in its current state. Their total output is 128 kilojoules, 6% of the planned final capability. The next step would be testing them, the official said. When it comes to building lasers to cause nuclear reactions, the larger the better, says Stefano Azzini, a physicist at the University of Rome, Italy. Larger facilities can produce higher energies, meaning materials can be subjected to higher temperatures or pressures, or that larger volumes of materials can be tested. Expanding the limits of experiments potentially gives nuclear researchers more useful data. In experiments, these lasers blast their target materials into a high-energy state of matter known as plasma. In gases, solids, and liquids, electrons are usually locked tight to their atoms' nuclei, but in plasma they roam freely. The plasmas throw out electromagnetic radiation, such as flashes of light and X-rays, and particles like electrons and neutrons. The lasers therefore also need detection equipment that can record when and where these events happen. These measurements then allow scientists to extrapolate how a full warhead might behave. So far, Russia's lack of such a laser hasn't been a great disadvantage in ensuring its weapons function. That's because Russia is committed to continuously remaking plutonium pits, the explosive cores found in many nukes, named after the hard centers of fruits like peaches. If you can readily replace old explosive pits with new ones, there's less need to use lasers to check how much they have degraded over the years. In the US, we would be remanufacturing our nuclear weapons too, except that we don't have the capacity to produce large numbers of pits, says Lewis. The largest US production facility, in Rocky Flats, Colorado, closed in 1992. Advertisement. Researchers have used lasers in nuclear weapons testing since at least the 1970s. At first, they combined them with underground tests of actual weapons, using data from both to build theoretical models of how plasma behaves. But after the US stopped live testing nuclear weapons in 1992, while seeking agreement on the Comprehensive Nuclear Test Ban Treaty, it switched to science-based stockpile stewardship, namely using supercomputer simulations of warheads detonating to assess their safety and reliability. But the US and other countries following this approach still needed to physically test some nuclear materials with lasers to ensure their models and simulations matched reality and that their nukes were holding up. And they still need to do this today. These systems aren't perfect. The models they use to predict weapons behavior are not fully predictive, says Itsini. There are various reasons why. One is that it's extremely hard to simulate plasmas. Another is that plutonium is a weird metal, unlike any other element. Unusually, as it warms up, plutonium changes through 6 solid forms before it melts. In each form, its atoms occupy a very different volume than the preceding one. Nevertheless, aside from actually detonating bombs, laser experiments offer the best way of predicting how nukes will perform. The US completed the NIF in 2009 and started shining its beams on thin poppy seed-sized plutonium targets in 2015. That allowed scientists to understand what was going on inside a weapon better than ever before. Laser experiments can also show how materials located near the radioactive pits in warheads degrade and react over their many-year lifetimes. Information from experiments can also help reveal how these materials perform in the extreme temperatures and pressures of a nuclear detonation. Such experiments are indispensable for designing and engineering components of nuclear weapons, says Vladimir Tikhonchuk, emeritus professor at the Center for Intense Lasers and Applications at the University of Bordeaux, France. Tikhonchuk has been following the Tsar Laser's progress since he saw it presented at a conference in 2013, the year after it was originally announced. He last spoke to scientists from Sarov at a summer school in nearby Nizhny Novgorod in 2019. He's skeptical that Russia will complete the laser. Russia certainly has the scientific pedigree. It has experience as a partner in building large scientific facilities, such as the multi-billion-dollar ITER experimental nuclear fusion reactor in Cadarache, France, Tikhonchuk notes. Russia also contributed components to 2 facilities in Germany, the European X-ray free electron laser in Hamburg, and the facility for antiproton and ion research in Darmstadt. And scientists at Russia's Institute of Applied Physics developed the fast crystal growth technology used in the lenses at the NIF and in the construction of all big lasers, Tikhonchuk says. But Tikhonchuk believes that Russia will struggle now because it has lost much of the expertise needed, with scientists moving overseas. He notes that the Tsar Laser's beam arrays are very large, at 40 centimeters across, which poses a significant challenge for making their lenses. The larger the lens, the greater the chance there will be a defect in it. Defects can concentrate energy, heating up and damaging or destroying the lenses. The fact that Russia is developing the Tsar Laser indicates it wants to maintain its nuclear stockpile, says Lewis. It's a sign that they plan for these things to be around for a long time, which is not great. But if the laser is completed, he sees a sliver of hope in Russia's move. I'm quite worried that the US, Russia, and China are going to resume explosive testing. The Tsar Laser investment might instead show that Russia thinks it already has enough data from explosive nuclear tests, he says. Wired approached the NIF and Rosatom, the Russian State Atomic Energy Corporation, for this story, but it did not comment.